Hi, my name is Chagai, and in this video we'll present the paper alias-free Convnets, fractional shift invariants via polynomial activations, a joint work with Tomer and Daniel. Before getting into details, here's a quick recap of the project. Although CNN classifiers were constructed to be shift invariant, in practice this is not the case. CNNs are in fact vulnerable to translation attacks due to aliasing and pooling and nonlinear layers, which break shift invariance. In this study, we show how to fix these layers to create an alias-free CNN. We do that by introducing a low-pass filter before pooling layers and by replacing general nonlinearities in an alias-free activation function. Our method maintains shift invariance and certifies integer and fractional translation robustness. Let's begin with motivation. We expect the output of a Convnet classifier not to be affected by translation of the input. In addition, we expect its internal representations to shift together with the input image. This implies that the classifier part of the CNN should be shift invariant and that the hidden layers be shift equivariant. Unfortunately, Convnets are not shift invariant and may actually change their output significantly due to even a single pixel shift. Although the basic building blocks of Convnets are indeed shift equivariant, pooling layers such as max pooling and strided convolutions break shift equivariance. The reason pooling breaks shift equivariance is aliasing. Without sampling, we can guarantee that our shift equivariant operations are equivalent to the same operations in the continuous domain. However, improper subsampling may violate the Nyquist theorem and decouple the discrete representation from its continuous counterpart. This problem can be partially solved by introducing a low-pass filter before subsampling. However, if our CNN has pooling layers, we may still have aliasing due to pointwise nonlinearities. The problem is illustrated in the following video. On the left-hand side, we have a continuous bandlimited signal Z. In the middle, applying real U yields a non-smooth signal. Next, we downsample both signals and reconstruct the continuous signal again. While the smooth original signal is perfectly reconstructed, the post-activation signal suffers from aliasing, and as a result, it is distorted by translations. However, applying a low-pass filter on the post-real U signal in the continuous domain yields a band-limited signal again, and it can be sampled and reconstructed without aliasing. Equipped with this observation, we construct an alias-free convnet based on Convnet's architecture. First, we replace all strided convolutions with convolution followed by blur-proof layer, which applies a low-pass filter before subsampling. Next, we replace the GLU activation function in a polynomial, which is applied after upsampling. This mimics applying the activation function in the continuous domain, which prevents aliasing. In the paper, we show that these changes construct a CNN which is invariant to integer as well as fractional shifts. Next, we describe why our activation function is alias-free by observing the frequency domain. Suppose our discrete input represents a band-limited continuous signal. Thus, its frequency response contains non-overlapping replications of the continuous signals. Upsampling shrinks its frequency response and expanding the allowed frequencies. Here, applying the polynomial activation expands the frequency response support by a finite factor d without causing aliasing in the relevant frequencies. Thus, the discrete signal remains a faithful representation of the continuous signal after applying low-pass filter and downsampling back to the same spatial size. In contrast, applying a nonlinear layer such as GLU expands the support infinitely. This leads to aliasing, interference in the relevant frequencies. This causes the discrete signal not to be a correct representation of the continuous one after low-pass filtering and downsampling. We now present the main results of our research. First, we show empirically that our model's internal representation is indeed shift equivariant by comparing the responses of half-pixel shifted inputs. The shifted internal representations in our model are identical, while in the baseline and APS model, which is invariant to integer shifts, the average difference per pixel reaches 50%. The following demonstrates how the output of our model is invariant to translations, whereas the baseline model may change its prediction due to a translation of the input. The perfect shift invariance of our model certifies its adversarial accuracy. Although our model suffers a minor accuracy reduction, its accuracy will not change due to adversarial translation attacks. In contrast, the baseline model accuracy drops due to integer adversarial translations. The APS model, which is robust as well to integer translations, loses accuracy when considering half-pixel or smaller fractional translations, for which our model is still robust. Although the certified robustness of our model is limited to circular shifts, our model enjoys improved robustness to other realistic translations, such as shifting the cropped area in an image. In this example, the output of the baseline model changes significantly as a result of minor translations, which leads to misclassification in some of them. In contrast, our model's output suffers only from negligible change and is less likely to change its prediction. In conclusion, our paper shows how to construct an alias-free convnet that is invariant to fractional shifts. This leads to state-of-the-art adversarial accuracy to fractional shifts. Interestingly, we do that with a polynomial network that reaches comparative results on ImageNet. Thank you.